Hello there guys, in this video I'm going to talk you through the solution and the mark scheme for this grade 9 GCSE circle theorems question. So just to talk you through what we've been told about here, we've been told that A, B, R and P are all on this circle here and that this circle has a centre at O. And we're also told that A, O, R and C are points on the circumference of this circle here. All of the lines that you see, so this one going through P, this one going through O, and this one going through R, are straight lines. Okay, and what we've been asked to prove is that angle CAB is equal to angle ABC. So just as a reminder, angle CAB is the angle you will draw if you join the dots from C to A and then to B. So from C to A and then to B, we're drawing this angle here, and then ABC from A to B to C, we'd be drawing this angle here. I'm just going to pop a dot on those two angles so we know the two that we're talking about. So we're trying to prove that those two are equal. So first thing to notice is radii. Okay, so if you're ever given a complicated diagram, I would suggest looking for radii first of all. So we know that O is the centre of the circle. So any line that goes from O to a point on the edge of that circle is going to be a radius. So OA, OB, okay, are both going to be radii. So those two orange lines we know are the same length as each other. We can also add some extra lines on that are radii. We can go from O to P, and we can also go from O to R. And to write that down in the proof, I could say OA equals OB equals OP equals OR because they are radii. So we know they're all the same length, which means that any triangle using two of those orange lines together must be an isosceles triangle. So two of the angles must also be equal, which is going to be useful for us later on. Okay, so I'm just going to say triangle POA is isosceles and triangle ROB is isosceles. Now, we're going to need to start thinking about using a circle theorem in order to help us out. So what you might want to do, particularly with a question like this that's quite complicated, is start thinking through your circle theorems one by one to try and find one that will work. You might be thinking about the angle at the centre being twice the angle at the circumference. We've got an angle at the centre, so that can be quite tempting, but we don't have any corresponding angles at circumferences, so that one probably isn't going to be helpful for us, but we might want to keep that one in the back of our mind in case it could come in later on. We haven't got any angles in semicircles using a diameter, so that one isn't going to be helpful to us. We also haven't got any tangents. This line here is not a tangent to the small circle because it goes through it twice. Okay, so because we're not looking at tangents, automatically we can cross off the radius and tangent being at 90 degrees. We can cross off the alternate segment theorem, and we can also cross off two tangents from the same point are equal. So we're starting to narrow down what circle theorems could be useful. We aren't going to be able to use the bow tie theorem or angles in the same segment are equal because we haven't got that shape using four points on a circumference going from one to another, to another, to another, back to where it started. So we haven't got that either. What we're actually going to need to use is cyclic quadrilaterals. So I'm going to give you a minute, guys, to see if you can notice a cyclic quadrilateral using the four lines that we already have drawn and four letters that we already have. Okay, so the cyclic quadrilateral we can use is CAOR. This here is a cyclic quadrilateral. Okay, and we're using the fact that opposite angles in a cyclic quadrilateral sum to 180. So if we call this angle up here, the one we've got in with the blue dot on, X, then this angle down here that's opposite to it has to be 180 minus X. Okay, so we can say that CRO is 180 minus X and give the rule along with that for our proof. We've now got CRB, which is a straight line. Because it's a straight line, this angle here and this angle here together need to make 180 degrees. So we can say that angle ORB has to be X. Okay, because we said earlier on that ROB was isosceles, and these two are the same length sides, that means this one over here also has to be X. Okay, so we've now reached that point where this angle up here and this angle down here we have shown are both called X. So they are therefore both the same, and we've therefore proven that this angle is equal to this angle as required.